Hello, welcome to this screencast on higher order procedures in Ruby. And this presentation is based on the material by Nate Murray. I found this presentation on SlideShare and it was interesting. You can go to his blog. If you search for higher order procedures in Ruby, there is a tech.natemurray.com. And he has a link to the PDF slides you can download. Also, if you are interested in reading the original material, which was based on Lisp, you can watch the videos for free. And I'll be actually giving you some of my thoughts on this thing, and I will work through some examples to see how Ruby provides us a functional abstraction. To me, I would call Ruby as a hybrid language because it's not just object-oriented language. It has functional programming capabilities, and where objects have state and associated behavior, functionals are kind of have behavior and have state associated to it because of closures. And Ruby has closures, and we have functional abstraction. And this higher order procedure basically is this presentation is going to be about discovering functional abstraction in your code and making it more concise, and your program is at much higher level of abstraction. So let's get started. So the mathematical procedures are abstractions that describe compound operations on numbers independent of the particular numbers. For example, let's consider a cubing function. You cube a given number. Let's just call it x. X times 3 times, you get the cube. So this is capable of cubing any given number. So if you did not have this cube function, you would have to use multiplication, which is a primitive operator, and every time you need a cube, you need to multiply with itself 3 times. So this is at much lower level of abstraction, and it's not, you know, a good idea. We should actually operate as a high level as possible for the problem that we are solving. And our programs should be able to compute cubes, but our languages should not lack the ability to express the concept of cubing. It should allow us to, once we name that thing, what we are doing, we should allow us to provide the higher level of function. So one of the things that a powerful programming language should give us is the ability to build abstractions by assigning names to common patterns and then work in terms of the abstractions directly. So procedures provide this ability. Now let me just show you an example where we have a function that takes number a and number b. Return 0 if a is greater than b, otherwise it's going to call itself. So it's a recursive function. Okay, so this function computes the sum of the integers from A through B. We can call, let's say for instance, some integers from 1 through 10, and we'll just print this value, and the value is 55. Okay, in numerical processing, we need abstractions where we can take procedures as parameters, not just numbers. Same programming pattern will be used with a number of different procedures, and we will see what I have. I'll gradually build this thing up to show you what higher order procedures are when we get there. Okay, so and I will define what the higher order procedures are once I show you the solution to some of the issues that we encounter as we work through this example. Okay, next let's have another function, and this is going to be sum of cubes, and it also takes two parameters, and this is the, for any recursive function, this is the terminating condition, otherwise you'll be in a infinite loop. Cube A plus okay, now this function basically computes the sum of the cubes of the integers in the given range A and B. Let's find the sum of cubes, in this case 1, 3, and we'll just print them. We get 36 as the answer, and let's now move on to the third example. And this is going to be the value of pi by 8. This function computes the sum of the sequence of terms in the series which converges to pi by 8 very slowly. So it's basically 1 over some term plus 1 over some other term, 1 over, and it keeps on going. This fraction is added, and that will slowly converge to the value of pi by 8. So here is the function. Sum of a plus 4 comma b. Too many braces. Okay, let's compute one lower bound. Upper bound is 1000, and we'll multiply it by 8, and we'll print this value. So the answer is 3.139 and it goes on. That's the right answer. Okay, now we have three functions. So as you can see already, there are certain things which is repeating, and these are very identical. Okay, so the name of those methods are different, and this is also the terminating condition for the recursion is the same. And if you see, this is the first term, this is the first term, here is the recursive call, these are all the same recursive call, and this condition here which is being passed is actually the next value that would gradually get incremented or decremented till that value becomes greater than b. Then the entire function terminates and we get the result set. So this is the next value, and this term is actually the first term. Let's just call it as a term, and this is the value of a, this is the value b is the same, the upper bound is doesn't change at all. So if we make this thing as something generic, so it would look like this. The name of function takes two parameters and returns 0 if a is greater than b. Otherwise we have a certain function of a. In the first case, the function just, the term function would just return that a itself. In this case, it will cube that function and return the cube value for a, and so on. In this case, it does something else and returns that value corresponding to a. Plus, and then we have the recursive call, and then we calculate the next. This would be the next operation done on a to find its find the next value to be passed on to the recursive call. So when you're trying to remove those duplications by recognizing certain elements which is common and things that vary, this common pattern signifies that there is a useful abstraction waiting to be discovered. And if you see some of the mathematical notations which is actually equivalent to these things, it would use the sigma notation. Sigma a equals sigma a to b, and then that summation is going to go over either cubing or anything else that you're doing. So it's kind of independent of each other. And that abstraction used by mathematicians allows them to, operate at a much higher level. Okay, so as a programmers, we would need a language, that's powerful enough so that we can write a procedure that expresses the concept of summation itself, rather than only procedure that computes particular sums or anything else that you may be doing. And so how could we get rid of the duplication and operate at a much higher level of abstraction? That's what we are going to see now. So from here, what is the next step? We identified and have come up with a way of specifying the placeholders, slots, which can be varied to create all these different functions. How can we make it actual function which would vary? So let's do that now. So we have, let's say we want to find sum. It's basically kind of like a sigma, and it's going to take 4 parameters. One is the term that I have explained already, the lower bound, the next value, and then the upper bound. The next might be keyword in Ruby, so I'm using the next. And we would have the same condition like this here. And then we would be doing that term call with a plus, I'm just translating this abstract thing to a Ruby acceptable syntax. Think of it that way. And then I have the same function being called with the same parameters. I call the next, call with the value of v, a, and then the next argument, and then the upper bound. So that's how you would translate it. So let's get rid of this since this won't run. It was useful to get to this legal syntax for Ruby. And now, how can we write, the question is, this cubes function, how can we write the same function using this new sum function that we have created? Let's do a def. We could just take this guy, so we have sum of cubes a and b. Instead of doing this, we don't need this anymore because we already have abstracted the repetition here, defined it once there. So things that would vary in our case are, in this case, since we are doing a cube is nothing but using a function pointer here, method object, cube, and then convert that to proc object. That's the procedure. So cube, as you saw, this is the first thing we are defining. And then the next increment is going to be, it's incremented by 1. Okay, so increment, let's define the increment function. Cube is already defined here, so we are using this function. Okay, when you're using this as a symbol, it's going to find the method, return the method object for cube, and then we convert that to proc. And now we'll define the increment as increment something, means we add 1 and return that as the value. So increment value would be, we are basically converting that increment thing to proc objects, and then now we can call the higher level function that we have created here. Okay, so we can call the term is going to be, this is the term as I mentioned earlier, then we have already computed it, so we will pass in that cube, and then the lower bound, and then the increment, which is this thing, this guy here, and then the upper bound. as it needs the upper bound also. Increment is the next value and the upper bound. And let me comment out this one so that we can find the value of cubes using our new function. And there it is. It says 36, which is the same as what we had done earlier. 36. Okay, now that works. Now let's move on to the summing of the integers problem. So let's define sum of integers. That also is very similar to the sum of cubes. So we need to find the term, right? The very first term in the integers calculation is it's itself. So let's call that as just a method. You can name it anything you like. So we are going to use a fancy name called identity that takes the value of the lower bound and it just returns the same value. Okay. So we have sum of integers and the ID is self dot method identity converted to proc, and then the incrementer, let's see, incrementer is going to be the same thing, so we can reuse the same thing as we did here. And now we can call the sum that's being reused by all the other functions. So we have ID as the term, lower bound, and the next value, and the upper bound. And let's print the integers value for this thing like we did before and see if we can get the same answer. And it says 55. Did we get 55 here? Yes, we did. So that works. And we could do the same thing for the other example, PySum also, but you get the idea. So let's move on to the next concept. Now notice that this method is actually taking another procedure as the argument. Argument to these methods are now not just numbers, it's taking another procedure itself as its argument. Whenever you have a function which is actually taking another function as its argument, or it's returning a function as the value at the end of its execution, it's called that function, it's in this instance this particular function is the higher order procedure. So it allows us to operate a much higher level of abstraction. Okay, the next thing is this is like really small functions like identity and just returning the same value and incrementing. This seems to be like very trivial implementation in small methods. And why do we really need name for these things? And if I'm going to just use it once, And if let's say if this is a private function in your object, and if it's only being used within that particular object, and I don't really need to even define these things, I could use anonymous function, a nameless function that allows us to do the same thing. And that's what we are going to do now. So let's take the example where we did the sum. So sum cubes, instead of doing this, I'm going to nuke these two on demand basis. I want a cube function. Okay, to make it clear, so for the cube function, that's where we can use lambda. How do you want to cube this thing? The cube logic is going to be like this. Okay, the increment function is nothing but another procedure. Anonymous function is nothing but one added to it. So let's see if we can sum the cubes now again using this. Says 36. Is it true? Let's check this guy here. Yes. So we got the same answer. See how this function is actually passing in its arguments another procedure. So this particular thing is a higher order procedure. Now we'll see another scenario where the return value is actually a procedure. So one thing to notice before we go on is these examples, as you can see, it demonstrates how we can enhance the expressive power of a programming language. We can achieve even more expressive power by creating procedures whose return values are themselves procedures. Okay, that's the next in the item. And I'm going to actually clear out these old examples. Let's get rid of this. And let's move on to something more simpler than complicated mathematics. So even as we can define it as thing divided by 2, the remainder is 0. And I have another method, filter evens, and then I pass in a list. Let's say result initialized to empty array. I loop through each element. Save it in the result if that particular element is even. And then I return the result. So now we see the even numbers printed. And let's say I want to find the odd numbers or prime numbers. So basically, you want to apply a uh, certain condition, and depending on that condition, you, you actually have a list which is either odd, even, or anything else, like for instance, prime numbers. Okay, so you're varying the logic, and the result set varies. It's kind of like if you're using regular object-oriented programming, you would actually go ahead and create an abstract class, and you use maybe a strategy pattern or something. Here in a language like Ruby, everything is kind of like you can abstract just using the language. It disappears. Basically, it's not a limitation in the language that forces you to apply some design patterns to overcome the limitation of languages. It allows you to build abstractions. Okay, now, so what we need is a way of defining the algorithm the same, but varying what we are actually trying to accomplish. The logic, the condition that we need to differ. So how do we separate the implementation from the algorithm? So we need a way to filter the list based on certain condition. So let's call this as a predicate. So we'll have a method, make filter, that takes the condition, predicate, or whatever you may call it. And this guy is going to return a function. That's why this function is actually a higher order procedure. Okay. Result. It's very similar to the sequence of things I'm doing in the previous one. The difference comes now when I just call the predicate with that element to see if it satisfies the condition or not. If it does, this evaluates to true, and I'll save that particular element in the result set. Otherwise, I won't. And then I just return the result. So let's write filter odds equals make filter. I'm going to use this new function. I am going to pass a lambda to it. That is the predicate. Okay. So I define that predicate as if I divided by 2 does not have any, it's not equal to 0, then I define it as odd. Okay, now the make filter returns a lambda function. So this is basically filter odds. Let's just make it clear. Lambda function. And I can call this filter lambda. I can now call that method, since the block variable has list and it expects the list to be passed in. Okay, and since it returns the result list, we'll just print that. Filter arts lambda dot call call the list expecting n. Okay, there is a brace is missing somewhere. Make filter lambda. Okay, oh, I see. Okay, sorry about this. Do end. This another do end here. So, okay. Now let's print the value. There we got all the even numbers, odd numbers, sorry. See how we're able to identify where we need to use the blocks. We're not using the blocks just because it's cool. We are using it to raise the level of abstraction. So the power comes from the fact that this filter is not limited to numeric evaluations. Let's say we want to filter by numbers where the ordinal ends in the th, such as tenth. Let me show you. I have facets installed, so I can use the facet library. Teacher ordinal. So I just want to show you 10 dot ordinal will give you tenth basically. Facet integer dot ordinal. Okay, I have to do a require gems. Is it Ruby gems? Oh, crap. Okay, there it is. Okay, now you see tenth. That's what is happening there. Okay, now what I want to do is I want to filter all the it's filter it's I'm going to make my own filter that's going to pass in a lambda function. Using a regex, we will check if it's ending in it, th. Does it end in th? If yes, we will return true, otherwise we will return false. That's our logic for finding all the numbers which have the it's ending in it. Okay, now let's call this function. Since that make filter returned as a lambda, we can now call delayed execution with a list. Another brace is missing here somewhere. Oh, there is an extra brace, sorry. Okay, let's print that value and see what we, let's see what we get. 4th, 5th, 6th, 7th, 8th, 9th, 10th. There's no 1th. First, second is not there, so it works. So you saw how the power of blocks, when combined with this ability to pass multiple um, procedures as arguments into another function, or returning a procedure from another procedure, can be used to raise the level of abstraction. So we should learn how to identify hidden abstractions in our programs and to build upon them and generalize them to create more powerful abstractions. The best way to find abstractions is to see the duplication, being able to look at the code and be able to see the duplication emerging, and then gradually find abstraction. Otherwise you can actually over engineer and over abstract things, and that would lead to more complication than actually helping you. So the significance of higher order procedures is that they enable us to represent these abstractions explicitly as elements in our programming language, so that they can be handled just like other computational elements. So that concludes this presentation, and if you enjoyed it, please recommend me on working with Rails. Thank you. God bless.